Restoring electricity after a disruption is a critical responsibility for system operators managing large-scale power networks. In many advanced regions, electric grids are highly reliable due to rigorous standards governing their design, construction, and operation, as well as strong interconnections across countries or continents. However, despite careful planning, major outages, whether partial or total, can still occur. These may result from extreme events that surpass design limits, or from causes such as natural disasters, equipment failures, protection system issues, or human error. When such disturbances happen, they can lead to blackouts affecting wide, regional, or local areas, sometimes damaging key infrastructure or causing prolonged service interruptions. Rapid and effective restoration is essential to protect public safety, maintain social stability, and support economic activity. To manage recovery, control center personnel follow structured procedures and restoration strategies. These prioritize stabilizing the grid, energizing key transmission corridors, and gradually bringing generation units and customer loads back online. Success hinges on thorough preparedness. This includes operator training, clear procedural documentation, robust communication systems, verified black start capabilities, and reliable cranking paths. Power systems operate within defined boundaries and can shift between several recognized states depending on system conditions and constraints. These states reflect the system's stability, security, and ability to respond to unexpected events. While the exact definitions may vary by region or regulatory body, the general framework remains consistent. A commonly accepted classification such as that used by European transmission operators includes normal state. The system operates securely under standard conditions, even after expected disturbances, thanks to available corrective actions. Alert state, the system remains stable, but a potential disturbance has been identified. If it occurs, existing measures may not be enough to maintain normal operation. Emergency state, one or more security limits are breached, requiring immediate action to prevent further instability. Blackout state, part or all of the transmission network ceases operation, resulting in loss of power supply. Restoration state, efforts focus on re-establishing system functionality and ensuring safe, secure operation following a blackout or emergency. These states help operators assess system health and guide appropriate responses during major incidents. Understanding and managing transitions between them is essential for maintaining grid reliability and public safety. The primary goal of power system restoration is to bring the grid back to a stable and secure operating condition, ideally to normal or alert states, as quickly and safely as possible. This process aims to reduce downtime, limit economic and operational losses, and mitigate negative impacts on society. Although these objectives are widely shared across system operators, the level of preparedness can vary significantly. Differences in system design, operational characteristics, and market structures often influence how restoration strategies are developed and implemented. Insights from past incidents reveal persistent challenges, highlighting the need to explore new or adapted approaches that enhance both the speed and reliability of restoration efforts. This paper outlines commonly used restoration practices and introduces potential innovations designed to address specific obstacles encountered during real-world recovery scenarios. Across international practices, two primary strategies are commonly used to restore power systems after major outages: the bottom-up and top-down approaches. Bottom-up strategy: this method relies on black start generators units capable of starting without external power supply. It is typically used when the entire system is down and no support from neighboring grids is available. Restoration begins by energizing selected ultra-high voltage UHV transmission lines and forming isolated electrical islands. These islands are then gradually synchronized and expanded to restore load and system stability. Top-down strategy: this approach leverages support from interconnected neighboring systems. Operators first energize the main transmission backbone using external sources, then progressively restore local loads, restart generation units, balance supply and demand, and reconnect remaining areas. Given the complexity of restoration, including factors like black start unit availability, baseload generation e.g., nuclear plants, interconnection points, substations, telecom infrastructure, and communication protocols, system operators routinely develop and update detailed restoration plans. These plans must align with regulatory standards and operational requirements. Because each method has its strengths and limitations, many operators adopt a hybrid strategy, combining elements of both approaches to suit their specific grid configurations and regional conditions. Real-world implementations vary, reflecting the diversity of system designs and operational philosophies worldwide. The Australian energy market operator AEMO oversees the reliability and stability of the national electricity market in EM, which spans multiple states. One notable event occurred in South Australia in September 2016, when severe weather including multiple tornadoes led to the collapse of transmission towers and a widespread blackout affecting approximately 850,000 customers. At the time of the incident, South Australia was operating with a mix of thermal and wind generation, along with imported power from neighbouring Victoria. AEMO's restoration target is to return the system to a secure state within 30 minutes of any major contingency. In this case, the restart process began about 42 minutes after the blackout, but initial power restoration took several hours. The restoration process begins with assessing the system's condition, identifying blackout zones, isolated generation islands, unavailable equipment, and necessary stabilization measures. Once islands are stabilized, AEMO and transmission network service providers (TNSPs) determine the restoration sequence, which may follow predefined regional procedures or adapt to real-time conditions. Initial steps involve energizing power station auxiliaries using black start units or available generation. This requires establishing cranking paths between black start sources and target stations. TNSPs and distribution companies then disconnect circuits and re-energize the transmission network with sufficient load to maintain voltage and frequency stability. Full restoration depends on available generation and the capacity of distribution networks to absorb load. South Australia's average demand is around 1,500 megawatts, and its wind generation has occasionally exceeded demand, posing challenges due to the high share of non-synchronous generation. To maintain system strength, AEMO mandates a minimum level of synchronous generation in proportion to renewable output. To ensure readiness, AEMO regularly reviews black start procedures with network operators and conducts annual training for transmission and distribution personnel. Brazil's national power grid, known as the Brazilian Interconnected Power System (BIPS), follows a two-phase restoration strategy: fluent restoration and coordinated restoration. The primary goal is to re-energize all transmission lines rated at 230 kV and above within 2 to 3 hours. Fluent restoration phase: in this initial stage, utility operators carry out control and switching actions based on predefined procedures. This allows for the independent and simultaneous recovery of key load centers without requiring direct coordination from the National System Operator, ONS. BIPS is divided into 44 fluent restoration zones. Coordinated restoration phase: if complications arise such as equipment unavailability, the process shifts to coordinated restoration. Utility operators then work under the guidance of ONS's regional and national control centers to manage recovery efforts across the grid. Hydropower plants are the primary source of black start capability in Brazil. For new hydro facilities, ONS evaluates whether black start functionality should be included, based on technical assessments during grid connection studies. If a black start unit is outside existing restoration paths, it may trigger the creation of new zones or integration into current ones. To ensure reliability, black start capable hydro plants undergo annual restoration tests under realistic conditions. These tests confirm operational readiness and help identify any equipment issues that may require repair or replacement. Before executing restoration plans, several technical studies are conducted: power flow studies, assess voltage levels, thermal limits, and reactive power margins across the grid during each stage of restoration. Electromechanical stability studies evaluate the dynamic feasibility of switching operations. Electromagnetic transient studies determine safe energization voltages and assess risks of transient overvoltages or resonance, especially during line energization or load rejection. To maintain operational readiness, ONS organizes annual training drills using operator training simulators (OTS). These sessions involve generation, transmission, and distribution operators across all regional control centers. Each drill covers at least one restoration zone and results in a technical report highlighting strengths, gaps, and areas for improvement, forming the basis for future action plans. India's power system restoration framework employs both bottom-up and top-down approaches, selected based on the nature and location of the blackout. The overarching goal is to restore supply as quickly and securely as possible. Bottom-up restoration utilizes black start-capable hydro and gas-fired generation units to energize isolated subsystems that are disconnected from the healthy grid. These units initiate recovery in areas without immediate access to external support. Top-down restoration applies to subsystems near stable grid sections, where power can be extended from neighboring healthy zones to restart generation and reconnect loads. Restoration priorities are clearly defined and typically follow this sequence: synchronizing island nuclear stations or providing startup power to nuclear plants, energizing thermal power plants, supporting non-self-starting hydro stations, restoring supply to critical services such as hospitals, re-establishing traction power for rail systems, building and synchronizing subsystems, reconnecting communication nodes and repeater stations, restoring supply to general consumers. India's grid is divided into 5 regional zones, each with its own state-level control areas. Restoration efforts begin independently across multiple locations, coordinated by state, regional, and national load dispatch centers to ensure proper synchronization and interconnection. A major blackout in July 2012 affected nearly the entire northern region, which had a load of around 38 gigawatts. Restoration was achieved using a hybrid strategy combining both bottom-up and top-down methods. Key challenges during restoration included maintaining real power balance and frequency control, especially under low inertia conditions, managing reactive power and voltage stability, including high voltage line tripping, ensuring proper functioning of protection systems and local controllers. To enhance future readiness, annual mock drills are conducted using black start units. These exercises typically involve creating and operating an electrical island with black start capability, simulating a blackout and restoring the island using bottom-up methods, resynchronizing the island with the main grid. Training sessions and post-exercise reviews involve personnel from dispatch centers, generation facilities, and distribution utilities. This structured approach has proven effective in improving preparedness and reducing restoration time during real events. Ireland's power system restoration strategy includes both top-down and bottom-up approaches. A key top-down resource is the East-West Interconnector EWIC, a high-voltage direct current HVDC submarine cable linking Ireland with Great Britain. Using voltage source converter VSC technology, UIC provides black start capability to both grids and is contracted by EirGrid, Ireland's transmission system operator TSO, to perform annual black start tests and participate in broader restoration exercises every 5 years. UIC, along with the AC interconnection to Northern Ireland SONI, forms the top-down restoration backbone. Bottom-up black start capability is provided by hydro, pumped storage, and open-cycle gas turbine generators. Restoration test using EWIC. May 2018, a coordinated test was conducted by EirGrid, UIC's owner IDAC, and the distribution operator ESB Networks with the following goals: initiate black start from the converter station, energize an isolated transmission path, manually synchronize the test system with the main grid, ensure system protection against short circuits and uncontrolled power flows. After EWIC was black started, it operated in island mode, controlling voltage and frequency independently. Transition to normal mode full power transmission was restricted until the connected system reached a short circuit capacity of 1800 MVA, a threshold determined during the interconnector's design phase. Since this level is typically hard to achieve in May, additional generators were synchronized ahead of the test. Synchronization was scheduled after the morning demand peak to stabilize frequency. Test sequence highlights: isolated transmission path prepared, AC supply to converter station disconnected, simulated low-frequency trip triggers black start mode, auxiliary power supplied via UPS and diesel backup, UIC energized at plus or minus 200 kV in island mode, HV switching energizes 400 kV and 220 kV bus bars, short circuit level confirmed above 1800 MVA, voltage and phase angles matched for synchronization, frequency controlled within 50 to 50.05 Hz, successful synchronization with 20 megawatts power. Flow to GB, UIC returned to normal mode and ramped to zero flow. Key findings are: short circuit challenge, achieving 1800 MVA short circuit level in a real black start scenario may be difficult, especially in the East region where EWIC operates. A new study is recommended to reassess this requirement. Frequency sensitivity. Even small frequency mismatches during synchronization can cause significant power flows. Tighter frequency control settings are advised for future black start operations involving EWIC. Power system restoration strategy. In Italy employs a top-down restoration strategy that relies on support from neighboring countries via the 380 kV transmission network. The goal is to quickly re-energize large thermal power plants, particularly those located in southern Italy, which are geographically distant from the core of the interconnected European grid. Execution time has improved through enhanced coordination with neighboring transmission system operators (TSOs), installation of shunt reactors for voltage control, and real-time monitoring via SCADA and WAMS systems. The Italian TSO, Terna, has conducted 5 full-scale restoration tests in collaboration with RTE France and Swissgrid Switzerland. These tests are essential for validating technical feasibility, refining restoration timelines, and ensuring operator readiness. Stakeholder coordination is critical to simulate realistic emergency conditions while avoiding disruptions to end users. Pre-test analysis and simulation. Before any real-world restoration test, detailed simulations are performed using offline steady-state and dynamic models. These include electromechanical analysis, evaluates generator performance, control systems, and synchronization behavior. Electromagnetic analysis assesses risks such as inrush currents, mutual coupling, transient overvoltages, and resonance effects. Simulations require accurate dynamic models and parameter settings, derived from equipment datasheets and field measurements. These analyses help identify potential issues and optimize restoration plans. Italy-France Restoration Test 2012, in a landmark test, Terna and RTE energized a 940 km transmission path from France to Valmontone in Italy within 25 minutes. The process involved synchronization of 3 hydro units near the French grid, 5 switching operations managed by Terna, pre-test electromagnetic studies to evaluate transient conditions and fault responses, use of advanced simulation tools modeling generator dynamics, line characteristics, and system interactions. The cranking path was modeled with frequency-dependent line representations, Marty's model, tower geometries, conductor properties, and soil conductivity. Special attention was given to phase sequencing and nonlinear behavior of shunt reactors and transformers. One key finding was that transient overvoltages during energization could reach up to twice the nominal voltage in the first cycle, especially near shunt reactors. These insights are vital for refining protection settings and ensuring safe restoration. Italy-Switzerland Power System Restoration Test. In 2013, Italy's transmission system operator Terna partnered with Swissgrid to conduct a top-down restoration test, building on earlier efforts with France. This test introduced 2 key advancements: use of shunt reactors only to energize a long-distance transmission path, first successful synchronization of a power plant located 1,000 kilometers from the Swiss grid. The 1,000 kilometers transmission corridor ending at Presenzano station, south of Rome, was energized in just 13 minutes, followed by synchronization of the Presenzano unit 4 minutes later. This rapid execution was enabled by a pre-compensated transmission path, segmented into 4 to 5 coordinated sections, each containing multiple substations and transmission lines energized sequentially. Measurement data confirmed that electrical transients matched predictions from offline simulations. The protection and control systems performed reliably throughout the test, validating both the technical design and operational readiness. Voltage recordings from Musignano, the first Italian substation on the path, aligned with expected phase-to-ground profiles, further confirming the test's success. In the United States, power system restoration planning is a collaborative effort involving system operators (SOs), neighboring operators, government agencies, and affected industries. These plans are regularly reviewed and tested to ensure the reliability of interconnected networks. Key elements include operational assessments, contingency procedures, and strategies to prevent transmission limit violations. While large-scale blackouts are rare, smaller weather-related events such as hurricanes have provided opportunities to test restoration protocols. The most significant recent example was the 2003 Northeast blackout, which originated in Ohio and cascaded across 8 U.S. states and parts of Canada, affecting over 55 million people. This event highlighted the importance of situational awareness and coordination, and led to improvements in restoration planning. Modern restoration strategies now account for logistical challenges, such as blocked transportation routes during major outages. Traditionally, ground crews were dispatched to assess damage manually. However, new technologies have transformed this process. Drones are now widely used to inspect transmission corridors, significantly reducing assessment time. Smart meters provide real-time data on outage locations, allowing operators to identify affected areas without sending personnel to individual sites. To support rapid recovery, SOs have identified critical transmission corridors and invested in structural hardening to protect against severe weather. They also maintain staging sites stocked with spare equipment, which must be located in areas safe from flooding or other environmental risks. Effective communication remains essential during restoration. While radio systems are standard, large-scale disruptions can challenge communication across wide areas. As a result, SOs continue to explore advanced technologies for resilient voice and data transmission to ensure coordination during emergencies. Recent analyses of major power system disturbances and blackout events indicate that operator errors are a leading contributor second only to natural disasters. The severity of these errors depends not only on the system's condition and available corrective actions, but also on the decisions made by operators and the effectiveness of pre-established defense mechanisms. Common causes of operational mistakes include limited situational awareness, inaccurate control decisions due to incomplete understanding or analysis, misinterpretation of system constraints, incorrect assumptions about protection system behavior, poor judgment of control action consequences, communication breakdowns. To address these challenges, mitigation strategies are typically grouped into two categories: preventive measures, designed to reduce the likelihood of operator errors through training, improved tools, and better system visibility. Impact reduction measures, focused on minimizing the consequences of errors when they occur, using automated defenses and robust contingency plans. Effective operator training, realistic simulations, and continuous improvement of procedures are essential to enhance decision-making and ensure reliable system restoration under stress. Future directions in power system restoration. Historically, transmission system operators (TSOs) have relied on conventional generators to maintain grid stability and support restoration. These traditional systems offered predictable behavior and centralized control. Today, however, real-time monitoring and advanced planning tools allow operators to assess system dynamics more precisely, especially in grids with high levels of renewable energy residential integration. As the energy landscape evolves, future power systems are expected to become more dynamic and less inherently stable unless new measures are adopted. Key challenges include reduced frequency stability due to declining synchronous inertia, volatile short-circuit power levels across the network, limited and dispersed voltage control resources. Currently, residential units offer minimal support for ancillary services like voltage regulation or balancing, and they are rarely redispatched for congestion management. Most residential technologies also lack restoration capabilities and remain largely unobservable or uncontrollable by TSOs, both of which are essential for coordinated recovery. Shifting restoration strategies. To adapt, system operators must transition toward a more decentralized and diversified restoration model. This includes enhanced coordination between TSOs and distribution system operators (DSOs), integration of new decision support tools and dynamic system analysis e.g., WAMS, DSA, leveraging power electronics for advanced control and restoration support. Impact of renewable energy and distributed generation (DG). The growing share of wind and solar energy introduces variability into the generation mix. Restoration efforts still rely heavily on conventional plants for stability, but future strategies must incorporate all available technologies, including distributed resources. As DG becomes more prevalent in distribution networks, restoration planning must evolve. The level of DG penetration and its controllability significantly influence the DSO's role. Role of power electronics in restoration. Power electronics interface devices (PADs) offer advanced capabilities that can enhance restoration efforts, including continuous voltage regulation, synthetic inertia, system restoration services, power oscillation damping. These technologies are embedded in various systems such as HVDC links, energy storage units, and fax devices e.g., STATCOMs. As their presence grows, PADs will play an increasingly vital role in stabilizing and restoring future power systems.
Role of HVDC links in power system restoration. High voltage direct current HVDC links offer valuable capabilities that can support power system restoration, particularly during black start operations and the formation of cranking paths. These links can assist with both active and reactive power regulation depending on their configuration and technology. There are two main types of HVDC installations. Inter-area HVDC links connect different synchronous zones and can transfer support from a stable region to one experiencing a blackout. Embedded HVDC links operate within a single synchronous area, often in hybrid AC-DC systems, and primarily manage power flow and voltage control. Although HVDC links have not traditionally played a central role in restoration, their involvement is expected to grow as grid technologies evolve. Technology types and restoration applications. Line commutated converter LCC HVDC. Based on thyristor technology, LCC systems offer high power capacity and efficiency. Capable of rapid active power regulation, useful for frequency control. Requires strong short circuit support and has a minimum power transmission threshold. Prone to commutation failures under weak grid conditions. Best suited for bottom-up restoration, especially as a large controllable load or generation source. Voltage-sourced converter VSC HVDC uses IGBT technology and offers flexible control features. Provides fast active power regulation without needing high short-circuit strength. Excels in reactive power support and has no minimum power transmission requirement. Immune to commutation failure, making it more reliable in unstable conditions. Suitable for both bottom-up and top-down restoration, including supplying power from a healthy grid to a blacked-out area, supporting reactive power needs using nearby generation or internal sources like diesel generators. As HVDC technologies continue to advance, their integration into restoration strategies will become increasingly important, especially in systems with high renewable penetration and complex grid dynamics. Role of energy storage systems in power system restoration. Battery energy storage systems (BESS) are increasingly recognized as valuable assets in supporting power system restoration. Their fast response capabilities make them suitable for various roles, including frequency regulation, load balancing, and even black start support. During restoration, maintaining a stable system frequency is critical to prevent further outages or cascading failures. Traditionally, small loads are reconnected gradually to avoid sudden frequency dips. However, this cautious approach can slow down the overall restoration process. BESS can accelerate recovery by acting as both a controllable load and a generation source, depending on their charge-discharge configuration. Studies have explored optimal sizing of batteries to provide effective frequency support during restoration. In South Australia, for example, large-scale BESS installations such as the 100 MW 129 MWh system at Hornsdale and the 30 MW 8 MWh system at Dalrymple have demonstrated their ability to deliver rapid frequency control. Notably, the Hornsdale battery responded within milliseconds to stabilize the grid after a major generator trip in December 2017. Beyond utility-scale systems, South Australia is also deploying virtual power plants (VPPs), integrating thousands of smaller batteries across the distribution network. Government initiatives aim to connect up to 90,000 batteries, offering around 400 megawatts of controllable storage. This expansion highlights the need for improved visibility and coordination within low-voltage networks, especially for voltage management. Energy storage can also serve as a black start source, supplying initial power to non-black start generators. One case study demonstrated a hybrid system combining BESS with a STATCOM, successfully delivering 27 megawatts of energizing power for 15 minutes, sufficient for initiating restoration. As storage technologies evolve, their role in restoration is expected to grow, offering flexible, fast-acting support across both transmission and distribution levels. WAMS in power system restoration. The integration of power electronics interface devices (PAIDs) has introduced faster and more complex dynamics into power system operations. To manage this complexity, wide area monitoring systems (WAMS) built around phasor measurement units (PMUs) are increasingly used by system operators worldwide. These systems enhance real-time visibility of grid behavior, improving situational awareness and supporting informed decision-making. Beyond monitoring, synchrophosor technology plays a valuable role in system restoration.
Unlike traditional SCADA systems, synchrophosors provide synchronized voltage phase angle data across different grid areas. This is especially useful when re-energizing or reconnecting sections of the network, helping operators assess system readiness and stability. During the restoration planning phase, synchrophosors combined with state estimation tools offer precise insights into the grid's condition, including island zones and available components. This data supports the development of effective restoration strategies. In the execution phase, synchrophosor inputs can be integrated into SCADA-based control modules to automate key actions such as load re-energization, island resynchronization, and generation ramp-up, ultimately reducing restoration time. Global applications and examples. In Europe, WAMS were used during the 2004 resynchronization of the UCTE zones and again in 2010 when Turkey was connected to the continental European grid. These events involved real-time dynamic assessments during critical synchronization phases. ENTSO Policy 5 outlines the procedures and responsibilities for such resynchronizations across its jurisdiction. In India, PMUs are actively used in control centers for real-time monitoring. Their time-synchronized signals allow control centers to mimic substation synchronization relays, improving coordination between generation units in different islands and enabling faster reconnection during mock black start drills. Italy also employs WAMS as part of its restoration strategy, as noted in earlier sections. As grid complexity increases, WAMS will continue to play a central role in enhancing restoration capabilities, offering both precision and speed in dynamic recovery scenarios. Evolving requirements for operator training systems. As power systems become increasingly complex due to technological advancements and changing grid dynamics, making accurate control decisions has become more challenging and the consequences of errors more costly. In response, electricity regulators are now emphasizing not only the certification of system operators but also the formal accreditation of their training programs. This shift demands significant updates to training tools such as operator training simulators (OTS) and dispatcher training simulators (DTS). These platforms must evolve to go beyond traditional knowledge delivery and foster new skills, decision-making capabilities, and adaptive thinking, especially in the context of system restoration. To meet modern grid realities, updated simulation models must accurately represent renewable energy sources and their control behavior, often located far from load centers, HVDC systems, fax devices, and protection schemes, customer load profiles, demand-side management, and energy storage systems. In parallel, new functionalities emerging in TSO/ISO control centers should be integrated into control center models (CCM) to enhance training realism. These include dynamic security assessment (DSA) tools, including real-time line and transformer ratings, operator awareness systems supported by wide area monitoring systems (WAMS), access to weather forecasting systems for operational planning.